Have you ever replaced a battery, starter, or alternator and the problem still wasn't fixed? Throughout my 15 years in the heavy duty trade, I've made my share of electrical mistakes, especially early on. But what if electrical wasn't so complicated? What if it followed a certain set of rules all the time? Well, it does. That's because electricity doesn't care what you think is wrong with the circuit, it only follows rules. And by the end of this video, you should understand the why of electrical system failures, not simply just what part to change. Let's start with the basics. Without getting too technical, electricity is the movement of electrons through a conductor. If electrons don't move, no electrical component can actually perform any work, and that's what we use electricity for, to do some kind of work. No movement means no work, just like fuel sitting still in a fuel line. In electrical, wires provide the path, electrons act as the workers, and loads are the machines doing the job. In heavy duty machinery, and automotive as well, most of the electrical is called direct current, or DC. There's a little bit of AC, or alternating current. That's what households commonly are wired with, which is AC voltage, but in this video, we'll be focusing primarily on direct current. So here's the next question. What actually pushes those electrons through the wire? That brings us to voltage. Voltage is simply electrical pressure. Imagine two batteries, one at 12 volts and one at 24 volts. Now, which one do you think can push electrons harder through resistance? 24 volts, right? Because higher voltage equals more pressure. Another important question is why do you measure voltage across a component instead of at it? It's because voltage is all about difference, not location. If the voltage isn't what you expect, power may not be reaching the load, or possibly it can't return to ground. If you've worked on any electrical, you may have heard an operator mention about certain problems, such as a ground problem or maybe a power problem that they're having. Well, guess what? Literally every electrical circuit problem is either a power or a ground problem. No power equals no circuit. No ground equals no circuit. A failed component, the electrons can't flow past the load to do the work, and they can't complete the ground circuit, so no circuit. But this leads us to a different concept called current. Current is the rate of electron flow, and that's measured in amps. Can you think of why a starter needs really thick gauge cables, but a sensor may only need just a little tiny wire to carry the load? That's because starters draw massive current, while sensors require very little. So if voltage is present but current can't flow, will the component work? Well, no current means no operation. So does that mean current gets used up by a component? Well, not exactly, as it flows in a complete loop back to ground. So, what controls how much current flows? That's the third part of the electrical equation, resistance. Resistance is anything that opposes current flow, and it's measured by a unit called ohms. But think about this, is resistance always a bad thing? Well, absolutely not, because components are designed to resist current flow to perform the work that they're designed to do. A small light bulb is basically a resistor that, when working, produces light, which is work that we want. But what about unwanted resistance? Yeah, that's not good for electrical circuits at all. This could include corrosion, loose connections, or damaged wires. So if you've ever seen a melted connector and wondered where that heat came from, it came from unwanted resistance in the circuit. Then why does a high resistance connection cause voltage drop? Because energy is being lost as heat instead of doing the work that we want it to do in the circuit. And this sets us up perfectly to discuss something called Ohm's law. Ohm's law ties everything electrical together into one simple formula. Voltage equals current times resistance, or V equals I times R. Why current is represented by an I don't know, but we will just go with V equals I times R. And this formula can solve every electrical problem you have, no joke. For simplicity, we'll start with a very simple circuit of one 4-ohm light bulb. And we know our battery voltage is going to be around 12 volts. We know our resistance of 4 ohms, so we want to find out what the current is going to be. So if we divide 12 volts by 4 ohms, we will get 3 amps of current. If the resistance increases, but the voltage stays the same, what must happen to the current? Well, it's going to drop. With an 8 ohm resistance, 12 volts divided by 8 ohms equals 1.5 amps of current. But here's another example. Why do low voltage faults show up when connections get dirty? Well, that's because resistance is silently stealing voltage. That's why understanding this kind of theory matters. Are you diagnosing the cause or just reacting to the symptom? But let's apply this to some real circuits here. Every circuit needs power, load, and ground. Now, what happens if the power side is perfect but the ground is weak? Well, the circuit still fails, and that's because there will be high resistance in the ground portion of the circuit. But why do so many electrical problems disappear when you add a temporary ground cable? Well, that's because grounding is a crucial part of the circuit, not just simply an afterthought. If the electrons can't get back to the battery, is the circuit actually complete? Well, no. And if the circuit can't be completed, that means no operation, or at least not proper operation. For another example, let's just say a starter is clicking rather than firing up the engine. You might ask yourself, is voltage reaching the starter under load? Is current being restricted due to resistance such as corrosion in the cables? And is the ground path solid? Rather than guessing, what measurements would prove where the problem is? We'll get into this in a future video, but checking for voltage drop under load would be an important one here. This would check for proper voltage available at the starter while cranking and would identify if the cable between the battery and the starter is good. This is how technicians need to think, rather than simply replacing the starter and the vehicle not starting when actually it was the battery cable that had failed. So by now you should have an idea of why voltage alone doesn't mean that a circuit's going to work, why grounds matter just as much as power does, and why resistance causes voltage drop and heat. Do you want to be someone who replaces parts or someone who fixes problems? Check out this next video where we apply this theory using a multimeter to check for voltage, resistance, and amps, along with some basic electrical wiring diagrams.